Okay, it is recording now. So, today, the main reason behind this live session was that someone in actually the lab one, not this lab, reached out to me and said that they wanted to have a live session and at least the first lecture live session. So I decided to do it for you guys as well. But I guess I'm going to see you guys anyways in the propulsion class. So hopefully this live session will help a bit. If you guys had any questions about the syllabus, about the grading, and whatever questions you guys may have, please make sure to ask your questions, and I will try to do my best to answer the questions. Okay. So we talked about, let's start the class. Is there any questions before we start the class? No? Okay. So we talked about uh, if you had any questions, because I'm not going to see your comments or anything. If you have any questions, just turn on your mic and ask the questions. Okay. So we talked about let's see. We talked about all the grading parts and syllabus and everything. And your first lab, then we have to start discussing the first lab essentially. And as I've mentioned, there will be a little bit of difference between this lab and the lab one as far as the lectures go. So the lectures are going to be focused on the lab. So we are not going to go into that much details about the theory of the physics behind everything. We are mostly going to focus on the lab. We will have a lot of theory, but most all of them are going to be focused on the lab, not more than that. So we are not going to need more than 2 lectures, sometimes even less than 2 lectures a week. Okay. So let's just start with the uncertainty lab. Uncertainty lab is one of the labs we share with mechanical. They don't do it in mechanical anymore because they don't have the time, but this is essentially the same lab they do in mechanical engineering. And most of the discussion we're going to have in this lecture is something we have covered before in the aerospace lab 1, but since we are going to do a lab on it, I have to talk about them again. And yeah, also your lab is going to be, so we are going to finish the lecture about the next lab this week, but the lab itself is going to be on Thursday. So even before the next lab, we are going to discuss the material about the lab 2. So the lectures are going to be 1 week ahead of the lab, and make sure you are clear on that part. So the uncertainty analysis, let's start with the uncertainty analysis. The first thing you always need to understand when you are dealing with a set of data, with data set, if you will, is that your data is never accurate. There are always sources of error uh, and, and different sources of error that will make your data not accurate and not precise. But what's the difference between being precise and being accurate? So when your data is not accurate or not precise, what happens is that, let's say this is your true value. This is the thing you want to measure, right? Your measurements are gonna spread around this dartboard, if you will, right? They put a board, if you will. Well, when your data is not accurate, but it is precise, is that your measurements are not spread around. They are essentially pretty close to each other, but they are far away from your true value. They are far away from your true value. So you are precise, but your measurement device has a fixed error, for example. It always gives you a fixed error. And sometimes you won't be able to determine that fixed error because you don't have the true value of the measurement. Sometimes your measurements are accurate but not precise, which means that they are spread around. They are far from each other, further from each other compared to this one, but they all hover around the true measurements. So the red one is your true measurement, which you will never be able to measure. Essentially, you will always have some sort of error. And if your measurements, your data set is accurate and precise, essentially means that you are pretty close to the measurements and your measurements are not far from each other. Okay. So let's start with some, sorry. My keyboard is disconnected for some reason. Okay, sorry. So let's start with some definitions. What is data or data? Data refers to the information that has been collected from an experiment. So you have been collecting data in all of your experiments so far, and in some of them I asked you to do like the standard deviation calculations, the uncertainty analysis calculations, but it was never, our focus was never on the uncertainty analysis part itself, and this is the first time we're going to focus on it. So the data itself is just information that you record from experiment. It can, in our class, but it can also be a data recorded from, information recorded from a survey, a historical or an historical record, or anything else. The first thing you do to be able to represent your data is to find an estimate. Again, you will never have the, what happens? You never have the true values. What is going on? You never have the true value, right? Then you are never have it when you are dealing with measurements, right? So in order to be able to represent that true value, let's say you have 10 measurements, you have to find an estimate of this true value using those 10 measurements, right? And then you have to find the errors or uncertainties of your measurement that comes with the measurement and experiment, regardless of how careful you are. But what are uncertainties? Uncertainty, we have different types of uncertainties or errors, and two most common ones that you have to be familiar with is the systematic or bias error, which is a fixed error, and this is the reason your measurements may not be accurate or may be completely inaccurate, right? This systematic or bias error causes roughly the same amount of repeated uncertainty essentially in your data set. So if we go back to the representation here, doesn't matter how precise you are, this bias error, this is a perfect representation of bias error. It will always give you inaccurate results. Okay. There are also random or unbiased error, like a human error that comes into measurement. Let's say you are doing the measurements, the line that you're measuring is not straight enough. You have to straighten it a little bit. Fluctuations in the electronic instruments on the regular mechanical instruments. A lot of things that contribute to this, that this error, the random or unbiased errors, goes into your preciseness of the measurements. So if you see that your measurements are spread around, that will give you an idea that you may need to redo the measurements, right, to be able to make it as precise as possible. It is never you will never be able to completely have uh, a measurement without any precision error or unbiased error. It is not possible. So systematic or biased error and random or unbiased error will always be there, and your goal is to reduce them. But the thing with systematic error is that you are not able to reduce this error because you don't know the true value. You are trying to measure the true value of whatever you are measuring, right? You don't know it. If you knew it, then you don't need to do any measurements, right? You just knew the true value. At any point, if you guys have any questions, just ask, please. Just turn your mic on and ask, right? As mentioned before, it is very difficult, sometimes it is very difficult to distinguish between the two errors, especially when a situation like this happens, right? You don't know which one is the main source of error. Is it the precision error or the accuracy problem? Which one is the main source? Because your measurements are not accurate and also are not precise. Okay. We didn't have these problems in the previous class. Yeah, sorry, technical difficulties always there. So you engineers always should strive to know the validity and accuracy of the data they're measuring. And as mentioned before, eventually this is how you are going to present your data, because you never have the true value. You have a measurement which is going to be equal to your estimate of the true value plus minus the uncertainty of your result. So if you want to have a little more in-depth look at the definitions of uncertainty, we can actually present uncertainty as a function R that is a function of all of your measurements. So your uncertainty is going to depend on a combination of all of the measurements that you have made, right? And this uncertainty function is usually represented with WR. But how can we calculate the uncertainties of an independent variable, xi? Of course, we have to have a mathematical relationship. But what if we don't have the mathematical relationship? That's where statistics comes into play and the statistical methods. Okay, so we need to do the uncertainty analysis for the experimental data. But how can we calculate the estimate? So this is an estimation of the true value. Okay, it is not the real true value, it's just an estimation of the true value. How can we find this estimate? Because the only thing we have, the only things we have are the measurements, right? We have the data set, and that's it. We don't have the true value, we have nothing else. Okay, so what we need to do is essentially we have a scattered data, right? We already know that. Let's say these are the measurement, this is the number of measurement on this side, and this is the value of that measurement, right? You have for the first measurement you have this data, second one this, third one, and so on and so forth, right? What is the value of this estimate, which is going to represent your true value? Essentially, what we need to do is to find a central tendency here, right? And we are going to prove that central tendency is the best estimate for the true value later on. Okay, how can we find the central estimate? There are different types of central estimate. The first one and the most common one is the arithmetic mean, which is defined as x of m equals to 1 1 over n, which is the number of your measurements, sigma, or the summation of all of your measurements, right? The number of measurements here, the measurements themselves. Very simple. I'm pretty sure you guys are completely familiar with the arithmetic mean at this point. And it is essentially the average of your data, unweighted average at this point of your data. Okay. There are other types of definitions, or there are other ways of calculating the central tendency of your data. The first one is the median, which is a central value in a group of ordered data. So that is the most important part of it. Your data must be ordered. Okay, let's say it is, of course, out of the scope of this course, but let's say your the data they are measuring is the color of cars, right? Red, blue, yellow, whatever, right? There's no way you can have an ordered data there, because there is no, like, red is not better than blue. You may have a personal preference, but there is no objective reality to it. So, and since we are all dealing with numbers, for us, all of our measurements are, most of our measurements are essentially ordered. So that's not a problem for us. We will be able to find a median. And the mode is the most frequent value of the data. So let's take a look at this example. Let's say we want to calculate the median and mean. First of all, let's see if we have any mode. There we have 10 readings, and the readings are all different as far as I can say, right? We don't have any repeated data. So the frequency of each value on this table is just 1, right? So your mode, there is no mode, right? Because there is no data that is repeated more than others. There is no measurement that is repeated more than others. So there won't be any mode. But the mean, just use the formula, very simple, 1 over n, summation of all your measurements, 1 over 10 multiplied by 56, which is 0.13, which is going to be the summation of all of your measurements, and you will get 5.613 centimeters. But the median, to calculate the median, if you have an even number of data, which is the case here, we have 10 numbers, you find the 5th and the 6th essentially. And then you find the average of these two middle values. If we had an odd number of data, let's say if we had 11 readings, then the 5th number would have been the mode. Okay, so your mode is going to be, first of all, I forgot to mention this. You have to make sure that your data is ordered from the smallest to largest, or the largest to smallest, doesn't matter. But you have to make sure that your data is ordered first, then find the median. Okay, and your median is going to be 5.69, which is different from your arithmetic mean. We also have another type of another way of calculating the central tendency of your data, as it's called the geometric mean, x of g. Instead of x of m, which was the arithmetic mean, we have the geometric mean. It is mostly widely used in the biological processes or financial analysis. It is essentially the nth root of the product of n numbers. Right, so you essentially multiply all of your readings together and you take the nth root. It will give you your geometric mean. And each data point essentially is going to be seen as a scaling factor because you are doing the multiplication, and all are combined by increasing each other through the multiplication. Okay. And the most important assumption here for your geometric mean is that your data can be interpreted as a scaling factor. So, which means that your data cannot be zeros or negative. So in the geometric mean, when you want to use the geometric mean, you have to use that. You have to make sure that you understand that each reading is used as a scaling factor, right? So you won't be able to have any sort of zeros or negatives in your reading. Okay. There are a lot of advantages to using the arithmetic means, especially the skewed data or the compound rates. The main reason is that your arithmetic mean x of m is very sensitive to outliers. So the outliers is going to affect your arithmetic mean a lot, but they're not going to affect your geometric mean that much. For example, let's look at this data set. We have one reading of 1, we have 4 readings of 2, 3 readings of 9, and 1 reading of 90, which is definitely a huge outlier. Okay, if you want to calculate, the central tendency is, of course, is not toward 90 here, as should lie somewhere between 2 and 9, right? That's the central tendency of your data. But if you calculate the mean, your arithmetic mean will be 14, which is that your arithmetic mean will be skewed towards 90, which tells you that using arithmetic mean is not a very good representation. The arithmetic mean is not going to be a good representation of your data, essentially, the central tendency of your data. And the median is not sensitive at all to an outlier, which is not good as well, because you have the 90. 90 is there and must be represented in a way, right? Median here is 2 because that's the middle reading if you order your data, right? We have 1 ones, 4 twos. So let me write it down. The data are ordered from here to here. This is your first reading, second reading, third, fourth, fifth, 6, 7, 8, 9, right? So essentially your fourth reading is your median, right? Which is 2. And it's telling us it is not sensitive to outliers at all. So the best representation of a central tendency out of these 4 is geometric mean. Okay, so the takeaway from these definitions is that you have to know the characteristics of your potential data. If you have a huge outlier, you have to make sure that you understand that that outlier will affect your arithmetic mean. If you think that outlier is a mistake, you have to remove the outlier. And it is not just simple removing. You have to show that that outlier is a mistake, right? There are mathematical ways to do that. And if you think that outlier is not a mistake, you shouldn't use the arithmetic mean. And you have to choose the best estimate of the best estimate to represent your measurement. And we said this estimate essentially is the central tendency of your data. Okay. So for let's say we have these 2 different types of data sets. The central tendency of both of them are going to be x of them, right? Arithmetic mean, we don't have outliers here. We don't seem to have an outlier, and this is a distribution of your data. Essentially, let's say we have discrete readings. It means that these are your readings, right? So we don't have an outlier. We have many data points here and here, here and here and here and here and here, right? 2 different data sets essentially. But the arithmetic mean is the same. But so how can we differentiate between these two sets? Because these two data sets that are it looks like they are trying to represent two different true values, right? Not just one true value, two different true values. So we have to make sure, or even if they are trying to explain or represent one true value, their accuracy is different, right? So we have to make sure we show that. Right? How can we do that? Essentially by including the uncertainty part in the analysis. And the main difference, if these two data sets are trying to represent the same true value, the main difference between the two is essentially the precision. You don't know the accuracy at this point of the data point. You just know that the precision is different. And what it means is that, think about it this way, to understand why it is representing a different precision and a lower precision for this one. Lower precision for this one. Essentially, this distribution shows you your data is more scattered, right? Let's say this is your true value, right? So you have some data here that is furthest from your mean, right? And some data here that is furthest from your mean here, right? But the furthest data point from your mean on this other data set is here, right? Let's say this is your second data set. I think I have to change the color. You get the point, right? I'm going to call this 1, 1, and 2, 2. Okay. So these are the furthest data points. So this data set is more precise compared to the other one. Got a little confusing. But hopefully, if you guys have any questions, if you are confused, let me know. If not, we are going to move on. It looks like there is no confusion. So let's move on. And so the measure of dispersion of that data, how far they're from each other, from the mean essentially, is called the deviation. And deviation is shown with d of I. D of I, the deviation of a specific data from your estimate, which is your mean, is that data minus your mean. It's very simple. Let's say we want to calculate the deviation of this one here. The deviation is this from the mean, right? To find this deviation, you just have to subtract these two. That's it. Okay. And you can actually do this deviation for all of the data, and to find the average of these deviations, we can take the average essentially, and the average of these deviations must be 0, right? Just very simple arithmetic mean, if you will. You need to calculate di bar 1 over n. That's the number of data points for the deviation this time. Okay. And the summation of all deviations. Summation of all deviation is xi minus xm. Okay. So this proves to you if the summation of all the deviations are 0, which is 0, you can see the proof here, right? That's essentially this. Let me write it here. Sigma, we can make it sigma xi minus sigma xm. Okay. 1 over m, n, right? Sigma xm from 1 to n is n sigma xm multiplied by 1 over n is going to be sigma xm right here. And this part is just a definition of arithmetic mean. So x of m, just subtract those two. you will get to 0, right? So the deviation of all of your readings, the average of these deviations, is 0, which means that arithmetic mean is a good estimate of all readings. If your data is not skewed, is it like normal distribution, and so on and so forth. So, but since the average of this deviation is 0, this doesn't really help us understand the uncertainty, the dispersion of data, right? How far your data is from this mean, right? Which of these measurements is more accurate? That doesn't help us with anything because the average of this deviation is 0 anyway. It's all for both of them, right? So we have to come up with this new way of representing the deviation, if you will, called the standard deviation or root mean square deviation, RMS deviation, right? When you have a large number of samples, more than 20 or 30, mostly more than 30, but in this course we deal with 20, only 20. And we can calculate the standard deviation by essentially di squared, right? Because this was di, right? Di squared. You take the summation of di squared multiplied by 1 over n, and then take the square root of it, right? This will give you the standard deviation. You can also calculate something called the variance by sigma squared, which is essentially the same thing without the square root of it. So we can have the variance, we can have the standard deviation. But if you are dealing with a small sample, in this class we're going to set it to 20, but you can prove that 30 should be the cutoff number. You can mathematically prove it. But we're just going to do 20. Because in your lab, I don't want you to do more than 20 measurements, more than 20, like 5 measurements. So let's say 20 is the cutoff value. If we are going to call the data sets with numbers, with the values, with the readings, number of readings less than 20, we are going to call them a small sets of samples. The standard deviation calculation is going to be a little different, right? On the denominator here, instead of 1 over n, we're going to have 1 over n minus 1. Okay, there are some reasons behind this. We are not going to go into details. I just should know this. And this is also called the sample standard deviation. Okay, so let's do the calculation. Let's go back to the example we solved. And previously, let's find the standard deviation. This only has 10 readings, right? So we have to find the sample standard deviation. But just to give you an idea of how they compare when you are dealing with the smaller samples, the standard deviation can be calculated to be 0.5944 centimeters, and the sample standard deviation can be calculated to be 0.627 centimeters. Okay, you may ask why we are changing the definition of a standard deviation. And as I said, I'm not going to answer with going into the proof of how the standard deviation is calculated and how the sample standard deviation should be calculated. But just keep in mind that the standard deviation itself is just a definition. It is not a real deviation, because if you do the real deviations, the average of those real deviations is essentially going to be 0 and it's going to be useless. So we have created this method to calculate the deviation from your data estimate, right? And just keep that in mind. So to represent that deviation better for a smaller sample size, we have changed the formula a little bit more. Okay, so let's do a review. Essentially, we are going to use the arithmetic mean as the estimate, and we have seen so far, let's say this is your true value, okay? We have seen so far that the arithmetic mean is the best representation, in our cases, mostly the best representation of the true value of the thing you want to measure. And a standard deviation is essentially an evaluation of the precision of your measurement, not the accuracy, okay? So the standard deviation for this measurement and this measurement, both of them, will be small, but that doesn't mean your measurements is accurate. So we are essentially here, we are only dealing with precision, not accuracy, okay? But then how can we have an idea of how accurate our measurements are? The best way is to have not just one data set, have like 3 different data sets. Let's say you have to do 20 measurements of something. Then you do 20, like 10 measurements of 20. So you essentially end up having 200 measurements, right? But in 10 independent data sets, right? And all of those data sets will have a mean, okay? And essentially we can calculate the standard deviation of that mean, right? Since we are calculating the mean, different mean, let's say, let's say we have this here. What we find one mean to be here, one mean to be here, one mean to be here, one mean to be here. You can calculate the mean of means, and most probably it's going to be closer to your true value, that the mean of means, okay? And the standard deviation of that means is going to give you a better understanding of your true value, essentially, and the uncertainty of your data. So essentially, we have to have an idea about the accuracy of the measurements instead of the precision. We have to do more measurements and we have to create more data sets. But you will be able to mathematically show that the standard deviation of the mean can be simply calculated by using just one data set and dividing it by the square root of the number of readings you have. So you don't essentially need to have 10, 20, 15 data sets. You essentially can have one data set and calculate the standard deviation of the mean. We can have an example, the same readings. We can find the mean, you can find the standard deviation, and the standard deviation of the mean, which is going to give you the best estimate of the deviation of your data set, and the best estimate of the accuracy of the system is going to be 0.1880. Okay, and keep in mind that we have used the regular standard deviation here, but we shouldn't have done this. We should have used the sample standard deviation, right? So here we should have had n minus 1. Okay. Again, going back to the review, the estimate is not, so the mean is not the same as the true value you want to measure. Okay. The mean is just an estimate of that value. And a standard deviation is an evaluation of precision. If you calculate the mean standard deviation, it will give you a better idea of the accuracy, but it is still not a measurement of accuracy. It is very important to keep that in mind. It will give you an idea about accuracy, but it is not the clear-cut measurement of your systematic error or systematic bias. Okay. So the next topic we want to discuss is how to do this uncertainty part. So far we know how to do the estimate part. We have an idea of how to do the uncertainty part of the measurement representation, but we need to talk about the probability a little more. So what I'm going to do is that I'm going to stop this lecture right now. and I'm going to continue the discussion in another lecture. I'm going to record that and put it online, hopefully by Wednesday, if not by Friday. And again, you are essentially 1 week ahead of each lab as far as the lectures go, right? So keep that in mind. Next Thursday, and by next Thursday, I mean, I'm talking about the Thursday, which is September 3rd, right? So this Thursday, not the August 27th, September 3rd. Oh, you don't see this. But yeah, September 3rd. We are going to have the first lab, and it's going to be the uncertainty lab. But by then, in the lectures, we are going to talk about the buckling test. So I don't know if you have gone over the syllabus, if you have watched the lecture, we have purchased a test setup to help us do the Euler buckling and it's the effects of see the effects of different types of support in Euler buckling. We did shell buckling, it was just a visualization. It is going to be a visualization for this semester as well, but you will do a full lab of Euler buckling hopefully as your second lab. Okay, so let me go all of this. Okay, is there any question, guys? Questions, guys?
I have a question.
Sure, go ahead.
How are quizzes going to work for this class?
Oh, that's a good question. That's I guess we should have talked about this in the didn't I talk about this in the first lecture?
Well, the audio was cutting out quite a bit, so.
Okay, yeah, sorry about that. I received an email actually from Trent about it as well. So make sure if you have any question, make sure to ask. So the quizzes are essentially gonna be let me bring up the syllabus. Where's the syllabus? Let's go to Blackboard. Okay. Do you see the syllabus now? I assume you do, so.
Yeah.
Okay. What is this? I don't want to start. Okay. So we are gonna have a quiz essentially every week, right? Mostly every week. But you're gonna have a quiz every week, every Friday, and that quiz will be an attendance. Most of them will be just attendance checks, just very simple questions like what is a standard deviation, for example, for this week, right? I just want to make sure that you have watched the lectures and you're like listening into the discussion we are having right now. Yeah, you know that there is a quiz and you have to answer those quizzes. But the quizzes that will be graded, these ones are essentially are questions from the theory of the class. For example, for the Euler buckling part, which is going to be your next second lab, you are going to get a question to essentially solve a buckling problem, right? To be able to calculate the buckling problem. Does that make sense?
Yeah, that makes sense.
Okay, and it's gonna be the same thing for all of them. So whatever theory you learn in the class, you will have to answer a quiz using that theory. It is gonna be harder to do that for the numerical parts, but you will learn a lot of mathematics in the numerical part. So essentially, these quizzes are mostly mathematical problems that you have to answer to. Some of them I may just ask you to like write a very small report. Like for example, I may ask you to tell me what is the difference in the especially in the numerical parts. What is the difference between like finite element, finite difference, and finite volume analysis? Just like a one paragraph answer. should suffice. So yeah, okay. Is there any other questions? The only part of the lab that I'm sorry, the only part of the labs that are still a little on we are still a little unsure about is this lab 9 and 10 essentially, which are the wind tunnel labs. And the instruments we have purchased for the wind tunnel labs are not here yet because of the COVID situation. It was a whole mess. Some of the, I mean, they shipped some of the instrument to my house. I had to bring them in. It was a whole thing. But this part, the wind tunnel, I'm not in charge of. Some other people are in charge of, and they've told me that they have purchased all of the instruments and the instruments should be in sometime in October or September. Yeah, so we should be able to perform these labs. But if we couldn't, then uh, what I'm gonna do is just I'm gonna do the numerical parts of the simulation. We are gonna do a numerical part of the boundary layer measurement and analysis. And maybe sometime next semester, I will send an email to you guys to be able to come and do the experiment without writing any lab reports, of course, but if you wanted to. Okay. Is there any other questions? No? So do all of you guys are all of you guys gonna come to the propulsion class? I know Haywood is not coming, and Trent, as I think he told me he's in Virginia. So Ryan, Tyler, and okay. So I know Josh is coming as well. So I'm gonna see you, the four of you, in a bit. And Haywood, the propulsion class is gonna be recorded, but I cannot upload it right away. So you just have to like wait until maybe tomorrow morning, even at the latest, to be able to watch the propulsion class. Okay. So if there is no other questions, okay. If there is no other questions, that's it for today. See most of you guys in a bit.